Okay, so let's take a look at 6.3, so development of quantum theory. So we saw that light is a wave, and it acts like a wave. Louis de Broglie said, okay, how about a small fast-moving particle or any moving particle? Can it also behave like a wave? So he developed this concept of basically saying that fast-moving particles can act like a wave and they can be treated the same exact way. So he developed this wave equation based on that concept. So the wavelength is equal to Planck's constant divided by the momentum. Those two things together are going to give us momentum. We have mass and we have velocity. It's important to recognize that that is not, in fact, frequency. So wavelength, we can apply a wavelength to a fast-moving particle. And so one more time, mass times velocity is equal to momentum. So again, there is energy in mass. And so the photon is essentially massless. We haven't really talked about that, but when we introduce mass, we have energy in the form of essentially a photon. So if we have a decrease in mass, we see an increase in wavelength. So ultimately what we have is small objects move fast and exhibit wave-like behavior. Great. So again, he has this equation where he's looking at the radius of, you can imagine an electron acting like a wave traveling around a nucleus with radius r, average radius r, wavelength between those two. Again, because we're dealing with something with nodes and these points here. So half wavelength, 1, 2, 3, 4, 5, 6. This one has 6 half wavelengths. So again, that value of n is going to be the number of half wavelengths. More importantly, we are seeing that we're restricted again to a specific number. So he applied this to fast-moving particles, or any particle for that matter. And there is an interesting YouTube video. If you check out PhD Comics and look at quantum mechanical, they show that they actually applied this to quantum mechanical models. Just as a quick aside, so if this is my wavelength of light, there are two terms that you might hear in physics in the future. So this is a wavelength of light. It's got a certain wavelength associated with it. And I'll use gray for this. So there is some wavelength associated with it. If it is red shifted, the term red shift is towards a lower energy. So if this wavelength was changed, if the energy of this wave changed, it might look something like this. Okay, so I got to keep going there. So this right here is the new wavelength. Notice that it's longer. Okay, that is a red shifted. So red shifted ultimately means it's shifted to a lower energy state, versus something that has been blue shifted, and blue shifted is something that shifts to a higher energy state. Wavelength is shorter, so this is called blue shift. Equals a higher energy. So if you ever hear the term, oh, something is red shifted or blue shifted, has a lot to do with like the Doppler effect. But blue shifted, red shifted, that's how we know the universe is expanding, because the light from further stars is actually red shifted because it's moving away from us, so it looks like it's a longer wavelength. Anyway, so the wave particle duality, we saw that light behaves like a wave, but there's no real mass involved. So Bell Labs, after the de Broglie thing, he basically said, all right, well, let's try this. Let's take an electron source. If it behaves like a wave, there are going to be these points where you're going to get reinforcement. So if the wave is going to propagate, it's going to propagate out like dropping a stone into a pond. If we drop two, if a wave reinforces, we expect this part to get double in size. But if it's the opposite, if they interfere, so this is constructive interference. And if they destructively interfere, essentially it's going to be just a straight line, so destructive. So when you have two waves that are propagating, you're going to get these areas, see where they overlap. This right here is constructive interference, and then you're going to have nodes in between. Ultimately, what you end up with is anywhere that they constructively interfere, you're going to have a line on our detector, and anywhere that they're destructive, you're not going to see a thing. So that is in fact what they saw. They see lines. So that's what we expect from a wave. And you can demonstrate this by just by looking at a pool. Well, if you take an electron source, if it acts like a particle, these things would go right through and they're going to hit here. This set of electrons is going to go through and they're going to hit right here, and you're just going to see two lines. But in fact, what they did see is they did see that it behaves like a wave. So those are the two possible sources, and this is kind of the definitive thing that says that although it's a particle, it does have wave-like properties. So electrons are, in fact, waves. So because we can apply this to large objects, consider a baseball pitched at 44.1 meters per second. The mass of the baseball is 146 grams. Calculate the wavelength. So if we calculate the wavelength out using the de Broglie wave equation, so wavelength is equal to h over mass times velocity. Again, we're going to look at units. So h is joules seconds. Mass is going to be in grams, and the velocity is in meters per second. Okay, and so actually, I believe we have to turn that into kilograms. Let me just double check. Yeah, we do have to turn it into kilograms. The mass is measured in kilograms because a joule is actually measured in, well, a joule is kilogram meter squared over second squared. Okay, so ultimately what you're going to have is second squared is going to cancel, meters is going to cancel once, kilograms is going to cancel, leaving you with meters as a unit. So 0.146 kilograms, and the velocity is good at 44.1. So let's just plug these in. So 6.626 times 10 to the negative 34 joule seconds over mass of 0.146 kilograms times the velocity of 44.1 meters per second. Again, seconds cancels, grams and meters cancel, leaving us behind just meters. You should end up with, if I did my calculations correctly, and I did. So you end up with 1.03 times 10 to the negative 34 meters. But again, that number doesn't really make sense to us at all. So let's convert that to nanometers. So times 10 to the 9th, you're going to end up with 1.03 times 10 to the negative 25th nanometers. That number is nothing that's a very tiny number. That's super, super, super energetic, right? Way, way too energetic. So this is too short to observe. So something strange here is, yeah, this thing is massive, and you have to recognize that there is a ton of energy in mass. So if we had something traveling at that speed, because of the mass, it has a ton of energy. Although the wavelength is tiny, remember, wavelength to frequency, wavelength to energy, really short wavelength means it's really energetic. And this is in fact really energetic because it's a massive object, versus taking a look at an electron, calculate the wavelength of the moving electron, and we'll take a look at that. Okay, we'll do that in class. So Heisenberg uncertainty principle. This is super fancy. People hear this all the time. What is the Heisenberg uncertainty principle? I'm sure you have heard of Breaking Bad. And so Heisenberg, that's where you're it's where you're comfortable, or you've heard that name before. So it is a fundamentally impossible to determine simultaneously the exact momentum and position of a particle. I'm not going to go into solving the wave equation or anything like that. I'm just simply going to say that the position and the momentum, rho, there we go. So we have two terms. If I know the position or the momentum, I can't know the other. So it's impossible to simultaneously know. As in, if I knew where an electron is, there's no way for me to know the momentum. And if I know how fast it's traveling, there's no way for me to know exactly where it is. So the position times the momentum is equal to h bar, which is basically just the h bar is equal to I just want to make sure that I get this right. H over 2 pi. Okay, h over 2 pi. It's Planck's constant divided by 2 pi. But the momentum is equal to h bar over 2. And so this brings up the first issue with the Bohr model. The Bohr model is great for looking at electron transitions, but the Bohr model demonstrates a known location of an electron. So the Heisenberg uncertainty principle is going to contradict this. So Bohr locates electrons, and Heisenberg says that can't be true. So who is right? Well, the Heisenberg is correct here. So we use the Bohr model to demonstrate it, but we're really going to start looking at electrons as a probability more than anything. So let's start. This sends us down this road of quantum mechanics. Quantum mechanics, again, we have fixed positions for these things, but the momentum and the position are not known. So quantum mechanics and atomic orbitals. So the Schrödinger wave equation, which is going to combine de Broglie's hypothesis, where an electron acts like a wave, and it's going to represent what the probability of finding an electron is, as opposed to it's gonna instead of identifying where the electron, and then it's also going to include Heisenberg's uncertainty principle. So some fancy looking equations here. We're not going to get into it other than to say that psi is going to be our wave function. So whenever you see psi, that is a wave function. You don't really need to know anything about that other than the fact that it is a wave function. And it turns out if we take this wave function and we square it, this is the most important. This is the probability of finding an electron, which is really going to help us build our idea of what an atom actually looks like and give us some practical uses for it. So this is probably the most important thing to take away. So a wave function turns into the probability of finding an electron. Well, what exactly does that mean? So orbitals are defined by quantum numbers. And by the way, the Schrödinger wave equation is solved for a specific set of quantum numbers. So all of these quantum numbers that we're going to look at is the solution for this wave equation using that set of quantum numbers. And we're just going to leave it at that. Again, this is the important part. So an orbital is defined by a set of quantum numbers. These quantum numbers, which we're going to learn, are obtained by solving the Schrodinger equation. So these orbitals describe the region where you have a high probability of finding an electron. Ultimately, we put this wave equation into a graph, and what we have is something like this. So this right here is the demonstration of solving the wave equation, Schrodinger's wave equation. And what we find out is we have a spherical probability of finding an electron. So because we can't know the location, there is a 90% probability of finding the electron within that location. Okay. And in fact, this is a 1s orbital, and we're going to understand what that is in a little bit. But what this actually looks like is you have the probability of finding an electron, and you have the distance from the nucleus. So right here, there would be 0 distance from the nucleus. We would be right there in the center. So if that's the distance from the nucleus, our graph for the 1s might look like this. It's not a perfect distribution, because you're going to notice it drops to 0 on one side and doesn't on the other. But what we do see is this peak right here, there is which happens to sit at 52.9 picometers, is the most probable distance to find an electron. Again, this is the 1s orbital, which is spherical in nature. Again, we can't know the exact location. There is a 90% chance of finding it here. There's a 10% chance of finding it outside of here. What is the probability of finding the electron at 0, in the center of the nucleus on top of it? We have a node here. It hits 0, 0%. There is 0% probability of an electron. Okay. So it's the last time that we're going to really look at this in that much detail. If you look at some other formulas, you end up seeing that if you solve the Schrodinger equation in a couple of other instances for the n equals 3, the 3s, for example, which is also spherical, what you end up seeing is you see something along the lines of where we have, and those should be going all the way down. Actually, let me do this again. So this is like the n equals 3. It does start with the origin. This is the most probable distance to find the electron. And we have, in fact, 2 nodes in that 3s and minus. Yeah, so anyway, but we're going to talk about all of this. And in fact, we're going to make it much simpler. I just want to represent that. So let's take a look at the idea of quantum numbers. These are not bad. I promise you quantum numbers. In fact, we're going to walk through these again together. But these are quantum numbers. Oh, there, I just created it. So here are the principal quantum numbers. Okay, so each quantum number is going to build on the next one. Okay, so there are 4 quantum numbers, and each is going to build on the next one. So we're going to start with the principal quantum number. This is the one that we know already. So principal quantum number is the shell. Okay, so it is the shell. It defines the overall energy. Overall energy, and we're also going to say the size of the orbital. Okay, so size of the orbital. So principal quantum number n. N can equal 1, 2, 3, 4, 5, and on, all the way out to infinity. So we can have an infinite numbers, but we go with individual integers. So this right here is my principal quantum number, n. This will make more sense when we kind of put it all together. So what this ultimately means is n equals 1. This is n equals 1. In fact, n equals 1. This is n equals 2. This is n equals 3. Notice how it's bigger and bigger and bigger in size, greater and greater and greater energy. In fact, here's n equals 1. That's the proper distance. These are the maximum, or those are the high probability distances. Notice it's moving further and further away from the nucleus. Okay, so don't worry so much about the radii thing that we're seeing here. What we're just simply saying is n equals 1, n equals 2, n equals 3. They're getting bigger and bigger and bigger because it's moving further and further. Those electrons are moving further and further away from the nucleus. Good. Okay, so principal quantum number tells us size, tells us overall energy, and it's defined as the shell. Good. Okay, next up is the angular momentum quantum number, or the azimuthal quantum number. They use angular momentum, but azimuthal is another way that you're going to hear it. So before we had shell, now we're going to have the subshell. So this is within the main quantum number. So because it's within the same quantum number, we are going to use the value of n to define it a little bit. So subshell, it defines the shape. So it defines the shape of these things. And you have seen these before. So L is going to start at 0, 1, 2, 3, 4. And here is where it connects to the previous one. It goes all the way out to n minus 1. So it's going to go all the way out until you have. So as soon as you know n, you know how many possible subshells that you're allowed to have for the azimuthal quantum number. By the way, it's defined as just a script L. That's how we define it. So we have special names for these. And in fact, I'm going to look these up because I keep forgetting them. I know a couple, but I'm going to make sure I know it. So if L is equal to 0, that is known as the S subshell. If L is equal to 1, that is the P, 2 is the D, 3 is the F, S, P, D, F. So those are the ones that you know well. Those are the ones that we have actual experience with. By the way, the next one is G. I'm going to use a different color for that because you rarely see this one. The next one is G. In fact, we don't see it yet. So S, P, D, and F subshells. Okay, so those are the important ones. These two are synonymous. So if L is equal to 0, it is the S subshell. If L is equal to 1, it is the P subshell, so on and so forth. Okay. And this is going to be important because it's going to show us that we're by having these quantum numbers, just like energy is restricted, our values are going to be restricted as well. And we're just going to pause this for 1 second. Okay. Yep. So these things, the S, P, D, and the F, were named because of the spectral lines that they saw. So for S, they saw something that was very sharp. So this became known as S is equal to sharp. It's the visual impressions that's left. P is principal. D is diffuse. And F is fundamental. It's just a little bit of trivia. You never need to know that. But just so you know that those things do have a purpose. When you look at the spectral lines for these things, what you actually see is basically you see how what they look like in spectroscopy gave us these values. So I'm gonna erase that. There we go. All right. So I said that they had shape, they define the shape, and so let's take a look. So when L is equal to 0, which is our S subshell, and we've already seen 2 of these, it's just spherical. And I'm going to put a positive there. It's essentially the wave function is positive there. And we're going to talk about what that ultimately means later. But this is a sphere. Again, as we increase the value of, so this might be the 1s, the 3s might be much bigger, as we just saw. All right. When L is equal to 1, this is the P subshell. It looks like when you actually solve the Schrodinger equation, the shape that you get is kind of looks like a little barbell looking thing. One side is positive, one side is negative. The positive and negative basically just has to do, it's not like positive or negative, it has to do with the wave function sign at that point. It has a lot to do with symmetry. When L is equal to 2, we're the D subshell. There's a couple of different shapes. In fact, we're going to draw them all, but let's just start with the general shape for this thing. It's going to have these 4. It's going to kind of look like a 4-leaf clover, positive, negative, positive, negative. And then finally, when L is equal to 3, we have the F subshell, and we don't spend a lot of time out here. It's going to generally have 6. 1, 2, 3, 4, 5, 6. Positive, negative, positive, negative, positive, negative. So yeah, these are the shapes that we're dealing with. Something to note, the reason that these things are somewhat important, just in terms of, so if we code all of the gray or all of the negatives gray here. Negative, negative, negative. What you'll notice is, so for, if I start here and go across through the origin, it's the same sign. But here, if I go across the origin, it's the opposite sign. Here, if I go across, it's the same sign. Here, if I go across, it's the opposite sign. So these two change when you go through the origin. These two switch or stay the same. That has to do with you get to that in inorganic chemistry when you start talking about symmetry. But that is an important element of why those signs are there. All right. So last little bit on this, because this is kind of the buildup. So as an example of where we would actually use this, okay? If n equals. So if n is equal to 3, that means that L is equal to 0, 1, and 2, because n minus 1, so 3 minus 1 is equal to 2. So this is the maximum value that we can have for L. So it's possible to have a 3s, 3p, and a 3d. Can I have a 3f? I cannot, because it's restricted by quantum numbers. So if n is equal to 2, what are the possible L values can I have? Well, L can be 0 or 1. So it's possible to have a 2s or a 2p. I cannot have a 2d in this case, or I cannot have a 2. Yeah, I cannot have a 2d. So again, n feeds into L, which then feeds into the magnetic quantum number. The magnetic quantum number m sub L defines the orbital orientation. So again, this is going to give us the orbital. So we had shell, subshell. Now we're down to the individual orbitals within a subshell. So if I have a shell has multiple subshells. And each of these subshells is going to have orbitals. So it's kind of this hierarchy as we go out, and it's getting smaller and smaller. So it defines the orbital. More importantly, it defines the orientation of that orbital. So let's take a look. This is kind of one of my favorite things to do. First of all, m sub L can go from negative L by individual integers through 0 to positive L. Okay, so those are the possible outcomes for the value of m sub L. So when L is equal to 0, which is an S subshell, M sub L can equal just 0, because negative L being 0 and positive L being 0 just gives me one state. That means that in an S subshell, there is one orbital. Okay, and the S orbital, so if there's the origin, I can do this on here. It is a positive wave function. X, Y, in fact, those can be any, because that's a positive wave function and that's a spherical. So it doesn't matter if that's X, Y, or Z. That is my S orbital. That's it. That's boring, but it's what it is. Okay, next up. If L is equal to 1, M sub L can go from -1, 0, and +1. It can have, so in a P subshell, we can have 3 orbitals. The 3 orbitals are Px, Py, and Pz. X, Y, and Z. So Px is going to be a barbell positive, negative. In the X direction. Y is going to be, in fact, I think I'm just going to copy this so I can keep pasting it. So if this is X and this is Y, it's going to be a barbell in the P in the Y direction. And then the PZ is going to be a little bit different. X, Y, Z. You can imagine this is coming in and going out of the page. So that's going into the page and that's coming out of the page. Positive, negative. That is the PZ. Okay, Px, Py, Pz. So again, orientation. There are 3 orbitals, and there's no specific. This can be the Px, this can be the Py, this can be the Pz, the +1. So yeah, so Px can be -1, Py can be 0, and Pz can be +1. So it doesn't really matter. All of that's kind of up in the air. All right, next up, if L is equal to 2, I think hopefully we have this down here. Oh, we don't. If L is equal to 2, my M sub L values can equal -2, -1, 0, +1, +2. D, this is the D orbital or D subshell, giving us 5 possible orbitals. These are the ones we don't really talk about as much. In fact, organic almost ignores these completely, but there are 5 orbitals. So let's do it. So 1, 2, 3, 4, 5. And so we're just going to start, I'm going to start doing these. All right, so first one. The first 3 are actually pretty similar. 1, 2, 3, 4. Positive, negative, positive, negative. We're going to call this the X in the Y direction. This is going to be the DXY. It's in the XY plane. And you can guess we're essentially just going to do that again and again and again. In fact, I'm going to copy these. Just to give you an idea of they're exactly the same thing. So we're just going to change the origins. So So we had the dxy, let's call this x, and let's just shift the axes, call this z. So this is the dxz. Let's make this the y and this the z this time, dyz. So again, those three are basically just in between all of the axes. And then we have two other orbitals. These are a little bit higher in energy, but you guys don't need to know that. And this is in the x and then the y direction. So it almost looks like two p orbitals overlapping. Plus, minus, plus, minus. This is the dx squared minus y squared. What you'll notice the difference between those two, though, it's this one is on the lines, or this one is on the axes as opposed to the other. And then finally, this is the funky one. This is the one that looks very different. There's this little donut around, little spherical donut around the waist. Positive, that donut is negative, and that is positive as well. This is the z. This doesn't really matter, x or the y. This is known as the dz squared, which is actually dz squared minus y squared minus x squared. So there's more to it, but we just call it the dz squared. So those are the shapes that we have for the d. It's a little bit strange. The weird thing here, again, this donut sits in this xy, yx plane. So there's like this little conal node, which is a really rare thing, right? Each of these has some type of nodal location, right? Along the x-axis and the z-axis, we're seeing nodes there. In fact, coming out, we see nodes there as well. But yeah, so that's the d orbitals. So we've got one left. The last one is if L is equal to 3, M sub L can equal -3, -2, -1, 0, +1, +2, and +3. So this is the F subshell. There are 7 orbitals for this. And I would encourage you to just Google the F orbitals drawings and take a look. We don't get into them much. They're really complex and they're kind of crazy. They're complex versions of the D. All right, next up, the last quantum number, and this is the simplest one, thankfully. The last quantum number is M sub S. M sub S has 2 values. M sub S can be +1/2 or -1/2. Those are the 2 options for the magnetic spin quantum number. It defines as spin up or spin down. So if this is an electron, and the way that you really should think about it is, this is my electron, the little tiny particle. The spin up, it's not something that's spinning like upward. What's happening is it creates an electric field. So if it is spinning, if this, again, this electron is spinning in a counterclockwise direction, that counts as spin up. We would call that one the +1/2. If it is spinning in the other direction, we would call that spin down. Okay, so +1/2, -1/2. An orbital can hold a maximum of 2 electrons. So that brings us to the quantum numbers and what info that we just went through all of this. The reason that this is important is because what we want to represent is, if we were to take a look at, let's take a look at just the simplest, let's take the lowest energy thing, which is a 1s orbital. And if I take that orbital and I have 2 electrons in it, okay. And we're going to get to these different rules about these things. But this is a 1s orbital. So we can define these things. The 1, n is equal to 1. Well, I know if my n is equal to 1, that means that I am limited to L values. That means that L can only equal 0. And in fact, it does. This is my L value of equal to 0. So if we take a look at 1 electron, so if I isolate this electron right here, okay? This electron has its own set of quantum numbers. And this is essentially how we're going to be doing this in the future. In fact, we're going to be doing it shortly. So if this is electron right here, what is the n value equal for this electron? Well, it sits in a 1s orbital, so it has an n equal to 1. What is the L value? We've already defined that. L is equal to 0. Well, if L is equal to 0, that means m sub L can equal, there's only one value of m sub L that we can have, which is 0 as well. And m sub S, well, it's spin down, so we would call that -1/2. Those are the quantum numbers that define that electron. What about the other electron? What are the quantum numbers that define this electron? N is equal to 1, L is equal to 0, m sub L is also equal to 0, m sub S is equal to +1/2. If we take a look at this configuration, both of those electrons are going to have the same set of quantum numbers. This is forbidden. This is one of the rules when we start looking at electrons. That's forbidden. The same set of quantum numbers is going to be forbidden. And so that's pretty much how it's going to go. So if we take a look at an energy level diagram, initially we had the principal quantum number, right? So this is n equals 1. This is n equals 2, n equals 3, n equals 4. So again, these right here are the principal quantum number. Notice that they divide up, of course, too. So if n is equal to 1, that means if n is equal to 1, that limits my L values. So if n equals 1, that means that L is going to equal n minus 1, which is 0, and my m sub L, which is equal to 0. So that means that I'm going to have one subshell, and that one subshell has to be an S. And that means that I have one orbital within that subshell. And so there's my 1, principal quantum number 1, and we're going to call this the 1s subshell. Makes sense, I hope. So let's move up to the next line. So we know that we have n is equal to 2. Well, if n is equal to 2, then I have two opportunities here. I have L is equal to 0 and L is equal to 1. M sub L is equal to 0. So this is my 2s, and I only have one orbital there. So I would say if this is the 2s, how am I going to divide this? Let me move this around a little bit. If I call this my 2s, that's my m sub L value. If my L is equal to is equal to 1, -1, 0, +1. So this right here is my 2. The L equals 1 represents P. So this is my 2P. I have -1, 0, and +1. I have 3 orbitals there. And so it goes. The next 3s, 3p, 3d, 0, -1, 0, +1, -2, -1, +1, 0. Oops, sorry, not +1. 0, +1, +2. 5 orbitals. We can put electrons in all of these. And I think I'm getting a little, so that's the principal quantum number. So just to define it all up here. These are my shells. These individual lines, these individual levels are going to be my subshells. And then finally, the orbitals here, those are just going to be my orbitals. And this makes a ton of sense when you start putting together the periodic table in terms of what fills up. But yeah, this is a good place to stop. We're going to do some actual practical stuff after this, but quantum numbers are important.